أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture, we will discuss the differential form of first law of thermodynamics. This lecture is a part of the course Thermodynamics, having the course code of PHY331. From this lesson, we have some objective. We need to revise the first law of thermodynamics again, that is the law of conservation of energy. We need to understand the differential form of first law of thermodynamics. For that purpose, we need to do some calculation to develop the differential form of first law of thermodynamics, and at the end we need to understand the concept of heat capacity. Moreover, we can specify the heat capacity in the form of specific heat capacity. First part of this lecture is devoted to the differential form of the first law of thermodynamics. We know that if there are infinitesimal changes occurring in a process and there are infinitesimal changes occurring in thermodynamic variables or coordinates, then the process as a whole is called as infinitesimal process. We can write the law of conservation for such infinitesimal process, that will be equal to du is equal to dq plus dw. du is the amount of internal energy and dq is the heat given or taken up by the systems, and dw is the work done. So when du, the quantity du and dw are actually expressed in terms of thermodynamic coordinates only. If we consider the process to be a quasi-static infinitesimal process, so infinitesimal quasi-static process is the process moving from one equilibrium state to another equilibrium state slowly. Is actually the same quasi-static process, but the changes that are performed from one equilibrium state to another equilibrium states are very slow. So similarly, if we consider the above equation, the term du is actually the exact differential, but it is equal to the sum of two inexact differential, dq and dw. dq is not an exact differential. Similarly, dw, that is work, that is also not an exact difference. That is not an exact differential. So actually, internal energy is the property of the system, and that is why it is an exact differential. The terms dq and dw are not directly the property of the system. However, it refers to the surrounding when surrounding interact with the system and transfer energy in the case of temperature difference or some other things. How we can express dw in terms of thermodynamic coordinate? We can do it in terms of generalized force and generalized displacement. If we remember the last lecture, in the whole chapter we were discussing about the work done in different cases. So work can be expressed in terms of thermodynamic coordinate, and that thermodynamic coordinate are the generalized force and generalized displacement. Heat, that is dq, is not expressed in terms of thermodynamic coordinate, but later on in this chapter we will try to express the heat in terms of one of the thermodynamic coordinate, that is called as heat capacity of the system. So both dw and dq are not the direct exact differential of any particular system, though it is indirectly related to the system, because dw depends on generalized force and generalized displacement, and similarly dq depends on heat capacity of the systems. So based on this discussion, we can write the first law of thermodynamics in new forms for some particular systems, special systems. Just like we can consider a hydrostatic system, in that the first law of thermodynamics in this special form could be written as a du is equal to dq minus pdv. Pdv is actually the work done. Here U or internal energy is a function of 2 among the 3. These are actually the 3 variable systems PVT. Similarly, we have a stretch wire in which the first law of thermodynamics could be written as a d is equal to dq plus ta dl, and similarly for surface we have dq plus rho dA. For electrochemical cells, d is equal to dq plus epsilon dz, and for dielectric slab, the du is equal to dq plus et rho. And for case of paramagnetic rod, the first law of thermodynamics could be written as a d is equal to dq plus mu naught h dm. So we have particular functions, for particular thermodynamic variable in each of the system mentioned, and U directly depends on 2 among the 3 or 4 of variables, three variables present in this particular systems. So U is actually the exact differential of this particular systems. So the infinitesimal quasi-static process for hydrostatic system in terms of first law of thermodynamics could be written as, what we need to do, we need to replace the work done by PdV, because work done in case of hydrostatic thermodynamic process is equal to PdV, dW is equal to PdV. So in the last equation that was actually equal to dq is equal to du plus dW is replaced by dq is equal to du plus pdv. So here we can see that u is a function of thermodynamic coordinate pv and t. Is already mentioned in the last table that u is a function of thermodynamic coordinate pv and t. Among these three, 2 are independent while 1 is dependent on the other 2. So in this case the pressure is a function of v and t. So if we consider a composite systems that is composed of 2 different systems, just like we have 2 hydrostatic systems that are separated by diathermic walls, then the equation could be written as a dq is equal to du plus pdv plus p dash dv dash. So we have in this case the work done has 2 different parts because it's a complicated hydrostatic systems, and instead of 1, 2 different systems are involved. So the work done for each of the system is separately written, though the internal energy is same with each other, because the both of the systems are separated by diathermic walls, and diathermic walls means that it can easily exchange heat with each other. So if you consider the paramagnetic case, then in case of paramagnetic case, the dq or the first law of thermodynamics in special case could be written as a du plus pdv minus mu naught hdm. So in this case we can consider that u, that is actually the internal energy, it is a function of pv mu naught h m and t. So we have the other part of the lecture, that is something about the heat capacity and its measurement, how we can calculate the heat capacity and what is actually the heat capacity is. So we know that internal energy of the system could be changed by heat and work. If we can give heat to the system, the internal energy of the system could be changed. If the system do some work, the internal energy of the system is also changed. So it means that we can change the internal energy of any particular system by changing the heat of that systems or doing some work by the system or on the systems. So in some cases heat is produced from combustion or electricity passing through the resistors. The heat, we can easily produce heat when there is a combustion process or electricity is passing through the resistor, then due to some resistance some sort of heat is produced. Similarly, work can be produced from falling weights and compressed springs. If weight is falling, the gravitational potential energy is converted into work done. And similarly, if there is compressed spring, the energy that was used to compress the spring has been stored in the spring, and that has been restored when it is allowed to move. So the capability of a substance to store internal energy is actually the heat capacity of that particular system. The heat capacity is a special term that is used or expressed for a system to show its capability, its power to store the internal energy or energy for that particular systems. So if we can consider this term that is actually called as the heat capacity is not appropriate to be mentioned. It should be like internal energy capacity of any particular system, but from the very beginning it has been considered as a heat capacity. Therefore the notion heat capacity is used to express this idea, but actually and in reality is the internal energy capacity of any particular systems, because internal energy is the thermodynamic coordinate where heat is not. So therefore we can express it as a internal energy capacity of any particular systems. So heat absorption by a system may or may not increase the temperature. In some cases the heat absorption by a system can increase the temperature, but there are some cases as well where heat is increased, where heat is absorbed by the system, but the temperature of that system remain constant. There is no net change in the temperature of that systems. For example, if you consider a material and it's at its melting temperature, that cause no increase in temperature. If you are giving heat to it cause no increase in temperature. But if we consider some cases when the material is absorbing heat, when it is at somehow less temperature than its melting point, then it will give rise to the increase in temperature. So increase in temperature due to the heat absorption could be expressed in terms of average heat capacity. This is called as the average heat capacity, that is the increase in temperature of a body. So average heat capacity is equal to Q divided by Tf minus Ti, where Tf is the final temperature and Ti is the initial temperature of that particular system. So if we consider that the difference here, we can consider that Q, that is the heat, and change in temperature, that is equal to Tf minus Ti, becomes smaller, then the ratio approaches to a limiting value, or that the same heat capacity equation is further modified into this equation where limit is included in that. So the heat capacity is equal to limit Tf to Ti Q divided by Tf minus Ti. So at temperature, if we consider a Ti temperature, then the same equation could be written as a when Ti is so the C is equal to dQ divided by dt. The same equation is modified if we consider the change in temperature in this case. So this is the heat capacity. So extensive quantities such as volume or internal energy depends on mass of the systems. We discussed in previous chapter the intensive and extensive variable. In that, intensive were not depending on the mass of the system. So if we divide in two, its value remain the same, but extensive depends on the quantity or the mass of the system. So if we have extensive variable, then it depends upon, just like internal energy is also an extensive variable, then it depends the mass of the systems that should be considered. So if we consider the heat capacity, that is actually volume per unit mass or internal energy per unit mass, then this heat capacity is called as a specific heat capacity, and that is expressed in some particular cases. That is the specific heat capacity, and that is specific heat capacity is heat capacity per unit mass. So what is the specific heat capacity and how we can express it? Actually we know that it contains if we consider that a mole of any material, is this after specific heat capacity. We need to describe after specific heat capacity, that is the heat capacity per unit mass, we need to describe the molar heat capacity. And what is mole? Mole is actually a it contains as many elementary entities that are actually the atom, molecules, ion, electron, and other particle. Is their atom is around in 0.012 kg of carbon 12. So this number of atom of carbon 12 is called as Avogadro number, and it is represented by Na, and this magnitude is equal to as 6.022 multiplied by 10 to the power 23 particle per mole. So we have this amount of particle per mole. So if we consider this magnitude of carbon 12, so that has the value is equal to the Avogadro number, the particles per mole. So if the mass of an atom, that is actually called as a m, then the mass of the mole of an atom is called as mNa, because Na is the number of atoms included in that. So simply multiply m divided by m is actually the number of moles or the mass of an atom, mNa. So this is called as a quantity, is called as a molar mass of a material, and this is also called as a molecular weight of a material. So it could be written as m is capital molecular weight is equal to m is equal to small m into Na. Na is the Avogadro number whose magnitude is equal to 6.022 multiplied by 10 to the power 23. So the same molar specific heat could be written as a N is equal to total mass of the systems divided by capital M. Capital M is called as the molecular weight in this case. So this is actually called as the molar specific heat. So the molar heat capacity is given by C, that is represented by small letter C. The molar heat capacity is represented by small letter C. This is equal to the total heat capacity. Total heat capacity is represented by capital letters C divided by number of moles. So this means heat capacity per unit mole is called as the molar heat capacity. So capital C divided by N is equal to 1 over N dq divided by dt, because we have just put the value of capital C, so that is equal to dq divided by dt. So we have some other things that are relevant to the heat capacity, on which we can express the heat capacity, that is actually the heat capacity at constant pressure and constant volume. There are some restriction on the system, and due to this restriction the heat capacity of any particular system could be changed. So two of the common restrictions regarding the heat capacity of the systems are heat capacity at constant pressure and constant volume. If we consider the if we make the pressure constant in a particular process, then the heat capacity could be expressed as a Cp, and that is equal to dq divided by dt when pressure is constant. Similarly, if we have heat capacity at constant volume, then in this case we can consider the volume to be constant. So the expression for the heat capacity at constant volume is given as a Cv is equal to dq divided by dt, where the volume of the system is remain constant. So this is something about the heat capacity at constant pressure and heat capacity at constant volume. So the heat capacity of some particular system is given as if we have some general system, how we can calculate the heat capacity of that particular systems, and what are the notation for that. We have different general system that was the 1 dimensional, 2 dimensional, or 3 dimensional, and for that each particular case we can calculate the magnitude or the symbolic representation of heat capacity. Say for example, if we consider a hydrostatic system, then the same heat capacity, if it is at constant pressure, it could be represented by Cp, while in case of constant volume the heat capacity is represented by Cv. If we consider a stretch wire, then in case of stretch wire the heat capacity at constant tension is equal to theta, where the heat capacity at constant length is called as a Cl, because in this case the variable are ta and L. If we consider a surface, then in case of surfaces the heat capacity at constant surface tension is C gamma, and similarly the heat capacity at constant area is equal to Ca. In case of electrochemical cells, an electromotive force could be considered as a constant quantity, and that is equal to C into E small e electromotive force, and in some cases when we consider the charge to be constant, that the heat capacity is Cz. Similarly, for the case of dielectric slab, electric field may be remain constant, or we have a constant polarization that could be represented by C capital E in subscript, and similarly C and rho in subscript, that respectively. And at the end we have paramagnetic rod. If we have a paramagnetic systems and paramagnetic rod, and we need to calculate the specific heat, then it could be on constant magnetization, constant if we can consider the constant magnetic field or constant total magnetization. In case of constant magnetic field it could be represented by Ch, and in case of constant total magnetization it could be represented by Cm. So this is something about the heat capacity and mathematical forms or differential form of first law of thermodynamics. Thank you very much.